So the goal for the rest of the chapter is to continue our study of sheaves and see some common constructions with sheaves which mirror the corresponding constructions with modules. And a helpful tool when we work with sheaves is to know a bit more about their stalks, because in fact, these often determine all that we want to know about the sheaf itself. And so, for example, here's a helpful tool. If F is a sheaf of modules on X, then the stalk at the point P, so local sections around this point, is a module over the local ring of X at this point. Because having a local section and a local function, you can multiply them on the overlap where they are defined, and then you get a new local section. So we have these modules lying around, and then whenever we have a morphism of OX modules, then we also get a corresponding, first of all, map between the stalks by sending this section of F to the corresponding section of G via FU. And then this turns out not just to be an arbitrary map, but actually it is a homomorphism of OXP modules. And then an exercise is to show that, for example, if you want to check whether such a morphism of sheaves is an isomorphism, it suffices to check that it's an isomorphism at each stalk. And this is often something which we can check locally, maybe check on some affine neighborhood. And so in the following, when we look at different constructions of sheaves, there's kind of two different routes. First, we can stay on a single space X and then work with sheaves on there, maybe morphisms of sheaves. And this very much goes in this direction of homological algebra. So we are able to form sums, tensor products, kernels and co-kernels of such morphisms, and so on. This we're going to see a bit later. One thing that we're going to see now is that the good thing is once we have a morphism between two different spaces, it's also possible to move sheaves around. So we can either start with a sheaf on X and push it forward to Y, or start with a sheaf on Y and pull it back to X. And so this we're going to see, and kind of the certain sense easier construction is the push forward. And so for this, let F from X to Y be a morphism of schemes. This also works more generally. And F a sheaf on the domain. Then we say that the push forward F, is now a new sheaf on Y. And so we need to determine what it does on an open set of Y. So if you have U inside Y open, then, well, its preimage F inverse U is open in X. And then we just declare the sections here to be the sections of F on this preimage. So this gives us, for any open subset of Y, gives us such a set. And the restriction works fine. If we restrict to a smaller set here, then also the preimage gets smaller. And so we can restrict using the restriction of F. And this, first of all, defines a sheaf. This is not so hard to check. And this is called the push forward of F under the map F. And in fact, it is even an OY module, because, well, we just need to say, if we have also a function here, like a function lambda on this set U, and we have a section phi, which is a section of big F on this preimage, then how can we multiply them? Well, we can first pull back lambda under F, then we get a function here, and then we just multiply it over there using the OX structure, OX module structure on F. So this is a way we start with an OX module and we push it forward to get an OY module. Some examples. This now allows us to reformulate something that we have seen in a definition when we defined what a scheme is. Namely, when we define what morphisms of schemes are, so F goes from X to Y, then we had this data included, not just this continuous map, but also all these pullback morphisms from OYU to OX F inverse of U. And they had to be compatible with restrictions and so on. And now we can kind of see that this data here, so this OX of F inverse of U, this is exactly the evaluation on U of this push forward. And this has the advantage that now both of these sheaves, OY and F push forward OX, they are now sheaves on a single space on Y. So we can actually package all of this data as just saying we have a morphism of sheaves from OY to F push forward OX. And so we could give like an alternative definition and say a morphism between local Lie spaces XY is the data of this continuous map, and then a morphism of sheaves of rings on Y, like this, such that, and we have to have this local condition, so such that if you pull back this maximal ideal on IP on OXP, then you get the maximal ideal IFP on OYFP. And here, this pullback map is a slight variation of this map on stalks, which we have seen. So normally what you could do is, for this morphism here, this is a morphism of sheaves on Y, you get an induced morphism here at the stalk at FP. Then you would only land in this space here. And then you can check this space has a canonical map to any of the OXPs, like this. And then if you go this composition, then you say the maximal ideal here should pull back to the maximal ideal here. Okay, so that's just to say something which we have already seen and found useful before, namely this definition of morphisms of ring spaces and local ring spaces. This can now be formulated using this push forward. So this is one thing. And then another kind of important construction of a sheaf is if Y is a variety and P in Y is a closed point, then you get this inclusion morphism from the set containing P to Y. And well, the structure sheaf of the single point set is actually very easy to understand. On the point itself, the functions are just K. You just allow one constant in the field. And if you take the empty set, you always have to get 0. And so if you now take the push forward of this very simple sheaf here, then you get a sheaf on Y, like this. This is this push forward. And we can explicitly calculate what this sheaf does on any open set U inside Y, because it's just a section of OP on this pre-image. And then there's just two possibilities, as we see here. Either this pre-image is all of the point, which is the case if P is contained in the open set U. And then we get these sections. Then we get somehow the sections which are just some element of the field. And if P is outside of U, then we just get 0. So somehow this is a curious sheaf here on Y, which basically can detect if the open set that we evaluated on contains this single point or not. And this thing will be called the skyscraper sheaf of Y at P, because in a certain sense, like if you look at what the stalks do, they're basically everywhere 0 except at this point where they are K. And it's like a skyscraper, standing out from a very flat 0 surface. And we can then also see what does the pullback map here do exactly. Well, you start with some function on some open set U of Y. And well, if it doesn't contain P and you try to restrict it, then you just land in the 0 ring. You just get 0. If P is contained in U, then what happens is that this pullback just evaluates the function at this given point. And so somehow this, if you now package it in this data of this morphism from OY to I push forward of OP, then this pullback just sends phi either to its value at p if p is in U, or sends it to 0. And so somehow this is the picture. You start with some big function defined on a whole open set, and then you just basically restrict it on this single file. So this sheaf is called the skyscraper sheaf of y at p. And again, it's a nice, relatively simple sheaf to understand, but it surprisingly turns out relatively often in concrete calculations that we need to do with these sheaves. So this was the first in this series of constructions with OX modules.